Hello there, and welcome back to Silent Science, your quiet corner of the cosmos where curiosity meets calm, and science gently rocks you to sleep. Tonight, we're drifting once more through the vastness of space, not in haste, but in wonder. If you're here, you're probably already wrapped in blankets, eyes soft, thoughts slowing like embers at dawn. Good, settle in. Let your breath find its rhythm. We have all the time in the world, before we begin our celestial journey tonight. I'd love to know, where in the world are you watching from? And what time is it where you are? Drop me a line in the comments below. I'm always amazed by how many of us are drifting together from different corners of the globe. Whether it's midnight under city lights or early morning on a sleepy island, we're all looking up at the same sky or imagining it. Wherever we are, and if you enjoyed tonight's voyage, consider giving this video a gentle like and perhaps subscribing to the channel so you don't miss our next stargazing session. It helps more sleepy minds find their way here, just like yours. Now, tonight's story is a beautiful one. How galaxies, those sprawling cities of stars, are born from darkness and dust. I do hope it's not so interesting that it keeps you awake. But if it does, well, at least you'll know a bit more about the early universe before your morning coffee, so settle in. Let your shoulders drop. Breathe slowly. You're about to drift through 13.8 billion years of cosmic history. No rush. The stars will wait for you. 13.8 billion years ago. The universe was small, not just small in the way you describe a studio apartment with no windows, but unimaginably compact. Hotter than a star's core, denser than a physicist's calendar. During Nobel season, and then, in a moment that defies full comprehension, it began, not with an explosion exactly, despite the name. The Big Bang was more of a rapid, graceful swelling. Space itself expanded outward in every direction faster than the speed of light, like a balloon being inflated with a leaf blower set to cosmic. There wasn't debris flying through empty space. Space was the debris, and it was making itself as it went. In those first fleeting microseconds, the universe was a seething broth of fundamental particles. Quarks jostled with gluons. Photons zipped around like restless toddlers. And gravity, ever the patient sculptor, quietly began making notes. It was chaotic, blindingly hot, and extremely uncomfortable. Not a place for stargazing or marshmallow roasting just yet. But this early universe, for all its mayhem, was full of potential. Hydrogen and helium, the simplest, lightest elements, formed like cosmic Lego bricks snapping together from the charged chaos. These humble atoms would go on to build everything. Stars, planets, people, pet lizards, and of course, galaxies. About 380,000 years after the Big Bang, a mere blink in cosmic terms, something truly beautiful happened. The universe cooled enough for those atoms to capture electrons, forming the first neutral atoms. Light, which had previously been ricocheting around like a trapped firefly in a jar, was suddenly free to travel. This moment, known as recombination, created the cosmic microwave background, a soft afterglow of the Big Bang that still hums through the universe today. If your eyes could see microwaves, the entire sky would glow with the light of that ancient fire. But despite the glow, there were no stars. No galaxies, not yet. The universe at this point was a dark, expanding cloud of gas and potential. If you could drift through it, you'd see nothing but subtle ripples, tiny irregularities in the otherwise smooth distribution of matter. These ripples were everything. They were whispers of quantum fluctuations from the earliest moments, stretched across the cosmos by inflation. Some regions were just ever so slightly denser than others, barely a difference, really, but gravity noticed. And gravity does not forget. Over time, those denser pockets of hydrogen and helium began to pull in more and more material, slowly, gently gathering like cosmic dew forming on the spiderweb. These clumps, the seeds of future galaxies, were utterly invisible to the naked eye if eyes had existed. But they were already setting the stage for all the dazzling drama to come. It's a bit strange to think of the universe as quiet. But in a way, this era was no light from stars, no. Glowing galaxies, just the faint murmur of matter falling into itself. It was a time of stillness before the storm, a long breath in before the universe exhaled starlight. And yet, even now, with all our telescopes and equations, we're still piecing together how it all unfolded. How did these minute fluctuations lead to the sprawling grandeur of spiral galaxies? Why did some parts of the universe become bustling hubs of stars, while others remained vast, dark voids? The answers are written across the cosmos, in every glowing nebula and ancient star cluster. We just have to keep listening. The universe had just gone dark, not in the way a room does when the lights are turned off, but in the most complete sense. No stars, no galaxies, no glowing nebulae. Just an endless sea of hydrogen and helium gas, slowly being tugged by gravity into denser pockets. This was the cosmic dark ages, a long, quiet interlude in the grand cosmic symphony, a time when the universe seemed to be holding its breath. It lasted for hundreds of millions of years, perhaps as long as half a billion, and yet it was far from empty or uneventful. In fact, this era laid the groundwork for everything that followed. It was during this darkness that the invisible hand of dark matter began shaping the scaffolding of the cosmos, pulling ordinary matter along like threads in a vast, unseen tapestry. You see, dark matter doesn't glow, reflect light, or interact with anything except through gravity. That makes it notoriously difficult to detect directly. We've never observed it in a lab, and we still don't know what it's made of, but we can see its influence everywhere. And back then, during the cosmic dark ages, dark matter was already hard at work. Gravity is patient. It doesn't rush. It simply pulls, always has, always will. And so, over eons, dark matter clumped together under its own gravitational weight, forming what we now call the cosmic web, a vast, three-dimensional structure of filaments and voids stretching across the entire universe. Imagine the universe as a sponge, not the kind you use in the kitchen, but one that stretches infinitely in all directions. Some parts were slightly denser than others, tiny ripples left over from quantum fluctuations in the earliest moments after the Big Bang. These ripples, stretched across space by inflation, became the seeds of future galaxies. Dark matter gathered around them first, forming invisible halos. Then, pulled by gravity, ordinary matter, hydrogen and helium, fell into those halos, cooling and condensing into clouds. These clouds would later become the birthplaces of the first stars, but this process took time. A lot of time out there. Were no clocks in the universe back then. No sunrises, no days, just the slow, silent accumulation of mass. Gravity whispered, and the cosmos obeyed, and then finally something changed. In the densest pockets of gas, gravity won. The clouds collapsed under their own weight, compressing until temperatures soared to millions of degrees. Atoms pushed closer than they ever had before, and in that moment, unnoticed by any eyes, uncelebrated by any beings, a star was born. This was the first light since the Big Bang. These stars, known as population 3 stars, were unlike anything we see today. They were massive, some hundreds of times more massive than our sun, incredibly hot and extremely short-lived. Without heavy elements like carbon or oxygen to help cool the gas, they burned fast and furious, living only a few million years before collapsing into black holes or exploding as supernova. If you could have floated near one of these stars, you'd have been instantly vaporized. But if you somehow survived, you'd have seen the darkness begin to lift. One by one, these first stars pierced the ancient fog of hydrogen that filled the universe, lighting up their surroundings like distant bonfires in a cosmic forest. This period is known as cosmic reionization, a dramatic sounding name for a gentle process. The ultraviolet light from these newborn stars stripped electrons from neutral hydrogen atoms, ionizing them and making the universe transparent again. It was as though someone had cracked open the shutters of a greenhouse, letting light flood. And from our perspective billions of years later, we can't see these first stars directly. They're too distant, too brief, and their light too faint. But their fingerprints are everywhere. They transformed the universe from cold and dark to warm and glowing. They seeded the cosmos with the first heavy elements, the building blocks of everything more complex than hydrogen, including you, me, and the cup of tea you might be sipping right now, in a way. These stars were the universe's first artists, sketching the outlines of galaxies on the blank canvas of space, but galaxies still hadn't formed, not quite. These early stars were often scattered in small clusters, bound together by gravity, but not yet forming the grand swirling cities of stars we see in the night sky today. These were more like villages, proto-galaxies, testing the waters of structure and cohesion. Yet the ingredients were coming together, as these massive stars ended their lives in violent supernova. They blasted heavier elements into the surrounding gas clouds. Those enriched clouds cooled more efficiently, collapsed faster, and formed stars with greater ease. The next generation, population 2 stars, began to appear. Smaller, more stable, and already more familiar. And thus, the great cosmic cycle began. Gravity pulls and gas stars are born. They shine, die, and scatter their enriched contents. More stars form. Each generation builds upon the ashes of the last, layering complexity like stardust sediment. You might wonder how we know all this happened. If we've never seen these ancient stars, the answer lies hidden in patterns of light, like ghostly fingerprints left on the cosmic window pane. By studying the oldest galaxies, the chemical signatures in ancient stars, and the faint glow of the cosmic microwave background, astronomers can piece together the universe's childhood in astonishing detail. It's a bit like reconstructing the history of a forest by examining its oldest trees, its soil, and the direction of the wind. The clues are subtle, but they're there. And recently, we've begun to catch glimpses with telescopes like James Webb we're finally starting to see some of the earliest galaxies taking shape, small, chaotic, glowing clumps of stars from just a few hundred million years after the Big Bang. We're peering into the nursery where the first light bloomed. It's humbling, really. These stars lived and died before our solar system was even a dream. Their light traveled across space for billions of years, past colliding galaxies, past wandering black holes, past the growing Milky Way, until it landed softly on the mirror of a telescope pointed at the sky. And now it rests in your mind. In the quiet of your evening, as you drift toward sleep, the universe, once dark and quiet, had lit its first lanterns. The night had ended, and the age of galaxies was about to begin. Somewhere in the vast, dark ocean of the early universe, a single point of light flickered into existence. It was small, not in brightness, but in scale. Just one star among trillions to come. But this first star marked a turning point, a cosmic awakening after eons of silence. It wasn't alone for long. As gravity continued its patient work, more stars began to form, not scattered randomly, but clustered together like embers caught in a rising breeze. These were the first star clusters, tiny villages of light forming within collapsing clouds of hydrogen and helium gas. Unlike the stars we see today, these earliest stars had no heavy elements, no carbon, no oxygen, no iron. They were made only of what the Big Bang left behind, mostly hydrogen, some helium, and a whisper of lithium. Without heavier elements to help cool the gas, these stars formed much larger than most modern ones. Some were hundreds of times more massive than our sun, burning hot, shining bright, and living fast. These giants, known as population 3 stars, were unlike anything we observe now. They lived only a few million years, a blink in cosmic time, before ending their lives in spectacular supernova explosions. These explosions scattered the first heavy elements across space, enriching the surrounding gas clouds and setting the stage for the next generation of stars. But before we dive deeper into the lives and deaths of these ancient stars, let's take a moment to imagine what it would have been like to float near one of them. Picture yourself suspended in the darkness, surrounded by an infinite sea of invisible gas. You can't see much. There's no sunlight reflecting off your hands, no planets orbiting nearby. Just the slow pull of gravity shaping the world around you. Then suddenly a pinpoint of light appears, then another, and another. The sky begins to fill with distant bonfires, each one igniting in its own cloud of gas. The universe is still mostly dark, but it's no longer empty. Light has returned. These early stars didn't live in isolation. As more of them formed, they grouped together into small clumps called protoclusters, the first large-scale structures in the universe. These clusters weren't tightly packed like the globular clusters we see today. Instead, they were loose collections of massive stars scattered across expanding clouds of gas dot, and yet, even in these small gatherings, something profound was happening. The ultraviolet radiation from these stars began to ionize the neutral hydrogen that filled the cosmos. This process, known as cosmic reionization, slowly transformed the universe from opaque to transparent. The fog that had blanketed space since the end of the Dark Ages was beginning to lift out. Imagine watching this unfold, not with your eyes, of course, because the light would be too intense and the temperatures far too extreme, but with the mind's eye. A glowing ripple spreads outward from each star cluster, ionizing the surrounding gas like morning sunlight breaking through mist. Over millions of years, these glowing bubbles expand, merge, and grow until the entire universe becomes transparent again. This period marks the end of the cosmic Dark Ages and the beginning of the cosmic dawn, the era when the first galaxies started to take shape, but galaxies didn't appear fully formed. Like all great cities, they grew over time, starting with small neighborhoods that eventually merged into sprawling metropolises of stars. The first galaxies were not grand spirals or majestic ellipticals. They were irregular, chaotic, and often violent places. Gravity pulled gas and stars together, but the process was messy. Collisions were common. Gas clouds slammed into each other, triggering bursts of new star formation. Entire clusters of stars were flung into new orbits, reshaping the structure of these early protogalaxies. Some of these early galaxies grew quickly, devouring nearby gas and smaller star clusters. Others remained small and isolated, drifting quietly through the voids between denser regions. But no matter how they formed, they all shared one thing. They were built from the ashes of the first stars. Every supernova explosion sent shockwaves through the surrounding gas, compressing it and triggering new rounds of star birth. These later generations of stars, known as population 2 stars, were slightly smaller and more stable than their predecessors. They contained trace amounts of heavier elements, allowing gas to cool more efficiently and collapse into tighter knots. With time, even more complex structures began to emerge. Eventually, these early star clusters and protogalaxies merged to form the first true galaxies, vast systems of stars. Gas and dark matter bound together by gravity. Some became spiral galaxies, spinning gracefully with elegant arms. Others became elliptical galaxies shaped by past collisions and mergers, and some remained irregular, continuing to evolve in unique ways. This process of galaxy formation was not uniform. In dense regions of the universe where dark matter filaments intersected, galaxies formed quickly and clustered together. In sparser areas, galaxies developed more slowly, sometimes remaining isolated for billions of years. And yet, despite the differences in size, shape, and environment, all galaxies share a common origin. They were born from the same primordial gas, enriched by the same first stars, and shaped by the same invisible forces of gravity and dark matter. Even now, astronomers are studying these early galaxies using powerful telescopes like the James Webb Space Telescope. By peering deep into space and thus far back in time, they're catching glimpses of the universe as it was just a few hundred million years after the Big Bang. What they're finding is both familiar and strange. Some of these early galaxies appear surprisingly mature, already showing signs of structure and organization. Others are wild and chaotic, bursting with young stars and glowing intensely in the infrared spectrum. These discoveries are helping scientists refine their understanding of how galaxies form and evolve. But the story doesn't end here, because once galaxies formed, they didn't stay still. They moved. They collided. They merged. And in doing so, they continued to shape the universe into the rich, diverse cosmos we see today. So while we focused on the birth of stars and the emergence of the first star clusters, we're really witnessing the beginning of something much greater, the rise of galaxies, the building blocks of everything that follows. From here, our journey continues forward in time, tracing the evolution of these early galaxies into the majestic structures we see today, including our own Milky Way. But before we move on, take a moment to reflect. You are made of the same stuff as those first stars. Every atom in your body, the carbon in your DNA, the oxygen in your breath, the iron in your blood, was forged in the heart of a long-dead star. That ancient light you saw in your imagination, it touched something once, a star, a galaxy, a cloud of gas, and now it touches you. We are all part of this story, and the universe is still writing it. The first stars had lit the universe like distant lanterns in a sea of darkness, but they did not remain alone. As gravity continued its patient work, these stars began to gather, not randomly, but along the invisible scaffolding of dark matter that stretched across the cosmos like an immense cosmic web. The filaments of this web, woven from unseen mass, guided the flow of gas and starlight, drawing clusters of stars together into larger and more complex structures. These early gatherings were the first hints of something greater, not yet galaxies in the full sense, but the seeds of what would become them. We call them proto-galaxies, and they were wild, chaotic places. Unlike the elegant spirals or serene ellipticals we see today, proto-galaxies were rough around the edges, irregular clouds of gas and stars, constantly shifting and reshaping under the influence of gravity. Some were small, barely more than a few 100 million stars bound loosely together. Others were already on their way to becoming massive systems, feeding off nearby gas clouds and absorbing smaller clumps of stars. In these early structures, the universe was still learning how to build galaxies. Gas clouds crashed into each other, triggering bursts of new star formation. Some stars were flung outward by gravitational interactions, while others settled into stable orbits around the growing centers of mass. These early cores would eventually become the bulges of spiral galaxies or the dense hearts of elliptical ones. And then there were the supernovae. As the first generation of massive stars reached the end of their short lives, they exploded in brilliant flashes of light, scattering heavier elements across the surrounding space. Carbon, oxygen, magnesium, the building blocks of planets and life, were seeded into the interstellar medium for the first time. This enriched gas cooled more efficiently than pure hydrogen and helium, allowing it to collapse faster under gravity's pull. With each new wave of star formation, the process became more efficient. More structured. Was no longer just isolated stars forming in quiet corners of the cosmos. It was entire neighborhoods of stars, tightly packed, gravitationally bound, and growing fast. Some of these early star clusters merged with one another, drawn together by mutual gravity. Others remained separate, but orbiting within the same halo of dark matter, slowly weaving themselves into a single system. This merging process was not gentle. It was messy, dynamic, and often violent. Stars were pulled into new orbits, gas clouds collided, and shock waves rippled through the interstellar medium like cosmic tsunamis. But amid the chaos, order began to emerge. Patterns started to form. Some proto-galaxies began to spin, their rotation shaping the distribution of stars and gas into flattened disks. Others remained spherical, dominated by random stellar motions rather than orderly rotation. Still others showed signs of elongated shapes, early hints of the great galactic collisions to come. It was during this time that the foundations of galaxy morphology began to take shape. Spiral galaxies, like our own Milky Way, likely formed in regions where angular momentum was preserved, where gas could settle into rotating disks without being disrupted by major mergers. These galaxies continued to grow by accreting smaller satellite systems, maintaining their graceful structure over billions of years. Elliptical galaxies, on the other hand, formed in denser regions of the universe, where frequent mergers disrupted orderly rotation and scattered stars into random orbits. Many of the largest elliptical galaxies we observe today are believed to be the result of multiple major mergers between large protogalaxies, and then there were the irregulars, galaxies that never quite found stability. Some were young still, in the process of assembling. Others had been shaped by past interactions, pulled out of alignment by the gravity of passing neighbors. These galaxies were often rich in gas and bursting with new star formation, proof that even in the early universe, creativity was alive and active. One of the most fascinating discoveries about this era is that some proto-galaxies appear surprisingly mature, more developed than scientists expected given their distance and age. Observations from the James Webb Space Telescope have revealed galaxies that existed less than 500 million years after the Big Bang, already showing signs of structure and organization. This challenges previous models of galaxy formation, which suggested that such complexity should have taken much longer to develop. Now, astronomers are rethinking how quickly the universe learned to build galaxies, and what forces helped guide that growth. Dark matter played a crucial role. While it doesn't interact with light, dark matter's gravitational influence was essential in pulling ordinary matter into place. Without it, the hydrogen and helium gas that filled the early universe would have remained too diffuse to collapse into stars and galaxies. Instead, dark matter acted as the hidden frame beneath the painting, shaping the cosmic landscape long before visible matter could reveal it. Supermassive black holes also began to make their presence known, though still relatively small compared to the giants we find at the centers of modern galaxies. These early black holes likely formed from the remnants of the first massive stars. As they grew by accreting surrounding gas, they released enormous amounts of energy, sometimes enough to halt further star formation in their host galaxies. This feedback mechanism, the balance between star formation and black hole activity, would go on to shape the evolution of galaxies for billions of years. But back in this early phase, everything was still unfolding. There were no grand spiral arms, no glowing nebulae lighting up vast dust lanes. There were only flickering clusters of stars drifting through expanding clouds of gas, slowly finding their place in the growing cosmic web. And yet, even in their simplicity, these proto-galaxies held the promise of all that was to come. They were the first drafts of galaxies, imperfect, evolving, and full of potential. From here, the story continues forward in time, tracing how these early structures grew into the majestic galaxies we see today. But before we move on, take a moment to imagine yourself floating among them, surrounded by clusters of young blue stars, bathed in the soft glow of ionized gas. Watching as gravity gently pulls everything together, you are witnessing the birth of galaxies. You are watching the universe begin to organize itself, and you are part of that story, made from the same stardust, born from the same cosmic processes. So, let's continue onward, deeper into time, as we explore how galaxies evolved into the breathtaking structures we know today. The universe was no longer just a scattering of stars and gas clouds. It had begun to organize itself, not neatly, not gently, but with purpose. Gravity, ever patient, continued its work, drawing distant clusters of stars closer together. What once were isolated proto-galaxies now drifted toward one another like dancers in a slow cosmic waltz, drawn by invisible threads of mass and momentum. Is the story of how galaxies grew, not just through steady accumulation of gas, but through mergers, collisions, and the constant reshaping of structure over billions of years. Galaxies are not solitary islands in space. They are part of a grand cosmic network, moving through the universe like travelers on an unseen highway. And when they meet, something extraordinary happens. When two galaxies approach each other, their gravitational fields begin to intertwine long before they actually touch. Stars don't crash into one another, they're too far apart for that. But the overall shape of both galaxies begins to distort. Long tails of stars stretch out into space, pulled by tidal forces like glowing ribbons unraveling from a gift box. These features are known as tidal tails, and they can span hundreds of thousands of light years, sometimes even longer than the galaxies themselves. They are the first signs of a collision, visible even from great distances, telling astronomers that two galaxies have met and are beginning to merge. But it's not just the stars that feel this encounter. The vast clouds of gas between them do collide, and when they do, something dramatic happens. Gas clouds slam into each other at incredible speeds, compressing and heating up. This compression triggers a wave of new star formation, a burst of stellar birth that can outshine the entire galaxy for millions of years. Astronomers call these events starbursts, and they mark some of the most intense periods of creation in the universe. Imagine watching this unfold from a safe distance. A galaxy caught mid-transformation, its spiral arms stretched and twisted, glowing with the fierce blue light of newborn stars. It's a moment of destruction and creation happening simultaneously, a reminder that the universe is always changing. Some of the most beautiful and chaotic galaxies we've observed are caught in this process. Take the antennae galaxies. For example, two spirals locked in a slow-motion embrace, their arms curling around each other like tendrils of smoke. Brilliant knots of new star formation glow like fireflies caught in a cosmic dance. These galaxies are not dying, they are becoming something new. Eventually, after hundreds of millions of years, the two galaxies settle into one another. Their individual identities blur, their stars scatter into new orbits, and what remains is a single unified system, often very different from either of its parents. And more often than not, the result is not a spiral galaxy anymore. Spiral structures are delicate things, easily disrupted by major mergers. When two large galaxies collide, especially if they are of similar size, the orderly rotation of stars breaks down. Instead of neat circular orbits, stars move in random directions, creating what we know as elliptical galaxies, smooth, round, and filled with older stars. This is how many of the largest galaxies in the universe came to be, not from peaceful growth, but from slow motion crashes between titans. Our own Milky Way has played host to many such mergers throughout its history. In fact, we can still see the evidence today. Stars from smaller galaxies that were torn apart and absorbed billions of years ago still linger in our galactic halo, orbiting in elongated paths like ghosts of long-lost homes. Even now, the Milky Way is in the process of merging with several smaller galaxies. One of the most notable is the Sagittarius dwarf galaxy, which is being slowly unraveled and absorbed by our much larger spiral. Its stars now trace looping streams across the sky, remnants of a galaxy that is slowly fading into the Milky Way's structure, but the most dramatic merger is yet to come. Our closest large neighbor, the Andromeda Galaxy, is on a collision course with the Milky Way. Right now, it lies about 2.5 million light years away, hurtling toward us at roughly 110 kilometers per second. That might sound fast, but in cosmic terms, it's a slow and graceful approach. We won't see the full impact for another 4 billion years or so. But when it happens, the night sky will change dramatically. Over millions of years, Andromeda will grow larger and brighter, eventually dominating the view. The two galaxies will twist around each other, their stars scattering into new orbits, their gas clouds colliding and triggering waves of new star formation. Eventually, they will settle into a new shape, likely a massive elliptical galaxy. Astronomers have already suggested a name for this future merger, Milkomeda, or sometimes Milky Way Andromeda, though Milka has also been floated, which sounds suspiciously like a brand of space yogurt, but we'll let it slide. Astonishing is that we can predict all of this from our vantage point inside the Milky Way, thanks to radio telescopes, infrared observations, and sophisticated computer simulations. We've been able to map the motion of stars, trace the distribution of dark matter, and even simulate the galaxy's fate. It's like piecing together a jigsaw puzzle from the inside and realizing the picture is much bigger than you ever imagined. So while galaxies may seem serene in photographs, elegant spirals, glowing halos, delicate dust lanes, make no mistake, the universe is not a quiet place. Out there in the vastness of space, galaxies are constantly moving, drifting, orbiting, pulled by gravity like dancers in an endless waltz. And occasionally, those dancers get a little too close. Their arms entangle, their paths cross, and they collide. Not with a bang, but with a slow, spectacular ballet that unfolds over hundreds of millions, even billions of years. Yes, galaxies crash into each other. But before you imagine stars exploding and planets smashing like marbles, take a breath. The reality is more poetic. Despite their size, galaxies are mostly empty space. Stars are spaced so far apart that even in a full-blown galactic collision, the chance of two stars actually hitting each other is vanishingly small. It's like watching two fog banks pass through each other, only the fog is made of stars, gas, dust, and dark matter, all swirling in gravitational fields. While individual stars may avoid direct collisions, the galaxies themselves do not emerge unchanged. When two galaxies meet, their gravity pulls and stretches them, distorting their shapes into long flowing tendrils of stars. Gas clouds, however, are not so lucky. When they collide, they do so with gusto, compressing, heating, and often triggering a dramatic burst of star formation. These so-called starburst galaxies can produce stars at rates dozens or even hundreds of times faster than usual. It's a cosmic baby boom sparked by the chaos of gravitational upheaval. Eventually, the two galaxies settle into one another. The final product is often not a spiral anymore. Spiral structures are too delicate to survive a major merger. Instead, the result is usually a large elliptical galaxy. The orderly orbits of stars are randomized, and much of the gas, once the fuel for new stars, is either used up in the starburst or flung out into intergalactic space. This is how many of the largest galaxies in the universe came to be, not from peaceful accumulation, but from slow motion crashes, like cities built by overlapping tectonic plates. But this isn't just ancient history. The Milky Way is not a passive observer in all this. It has its own collisions to reckon with right now. Our galaxy is in the slow process of merging with several smaller dwarf galaxies. The Sagittarius dwarf galaxy is being pulled apart and absorbed, its stars now tracing ghostly loops through the Milky Way's halo. Other small galaxies are on similar paths, being digested, restructured, and folded into our own. And then there's Andromeda, our nearest large neighbor. The Andromeda galaxy is on a collision course with the Milky Way. They're separated by 2.5 million light years, but moving toward each other at about 110 kilometers per second. That might sound fast, but in galactic terms, it's a slow and graceful approach. The collision won't happen for another 4 billion years or so, but when it does, the result will be spectacular. What will happen to us? Surprisingly little, at least on the scale of our solar system. Again, stars are so far apart that direct collisions are unlikely, but the night sky will change over millions of years. Andromeda will grow larger and brighter, eventually dominating the view. The two galaxies will twist around each other, merge, and settle into a new shape, possibly a giant elliptical galaxy. Astronomers have lovingly nicknamed the future merger Milka. Yes, really. Scientific naming has its moments of whimsy, but even before that grand dance begins, collisions continue all around us. Galaxies in dense clusters are constantly interacting. Their shapes are distorted, their gases stirred. It's part of the life cycle of the universe. Galaxies are not static islands. They evolve, grow, and change through relationships. Much like everything else in nature, what's especially fascinating is that these interactions aren't just destructive. In many cases, they're creative. Merges can restart star formation. They can feed central black holes. They can reshape the contents of galaxies in ways that lead to entirely new structures, like pruning a tree or mixing two colors of paint. The result is something new, messy at first, but often more vibrant than before. And in this ever-evolving cosmos, collisions are not the exception, they are the rule. We tend to think of the universe as calm and unchanging, a kind of eternal night sky sprinkled with frozen stars, but it's alive. Galaxies are drifting, falling into each other, blending. Their light, their stars, and their stories. Even now, somewhere out there, two galaxies are beginning their long, slow dance. One day, they'll collide. Non-violence, but in union, and a new galaxy will be born, just as it always has been. Just as it always will be. Even now, as galaxies drift through space like ships on a cosmic sea, they are guided by invisible hands. These hands don't glow. They don't reflect light. You can't see them in a telescope or photograph them directly. And yet, without them, galaxies would not exist. Not as we know them, not as grand spirals, not as majestic ellipticals, not even as scattered clusters of stars. They are the silent architects of the cosmos, dark matter and supermassive black holes. Let's begin with gravity, the most familiar of forces, and yet the least understood in its full cosmic role. Gravity is patient. It doesn't rush, it simply pulls. Always has, always will. In the early universe, It was gravity that noticed the tiny ripples left behind by quantum fluctuations during inflation. These ripples, barely perceptible differences in density, became the seeds of everything that followed. Gravity drew gas together, slowly at first, then more forcefully. It gathered hydrogen and helium into clouds, pulled stars into clusters, and eventually shaped those clusters into galaxies. But gravity alone wasn't enough. You see, if you look at a galaxy like the Milky Way and measure how fast its outer stars are moving, something strange happens. According to what we can see, the visible mass of stars, gas, and dust, those stars should be flung off into space like glitter from a spinning wheel. There just isn't enough mass to hold them in orbit, and yet they stay. They remain bound, loyal to their galactic home. There must be more mass than we can see, much more. This unseen mass is called dark matter. And while we still don't know exactly what it is, we know it exists because of how it affects the things we can see. It doesn't interact with light, which is why we can't observe it directly, but it exerts gravity, and there's a lot of it. In fact, dark matter makes up about 5 times more mass in the universe than all the visible matter combined. That means for every glowing star or swirling cloud of gas in a galaxy, there's a much larger invisible halo of dark matter holding everything together. Imagine a galaxy as a glowing jellyfish swimming through the deep ocean. Beautiful, delicate, drifting. But surrounding it is a giant invisible bubble, the dark matter halo, keeping the jellyfish from dispersing into the currents. Without this halo, the galaxy wouldn't survive. Dark matter didn't just help galaxies form, it gave them structure. It provided the scaffolding upon which ordinary matter could gather, cool, and condense into stars. Without dark matter, galaxies would have been smaller, less organized, perhaps even non-existent. So while we may never detect dark matter directly in a lab, we feel its presence everywhere, in the rotation of galaxies, in the way light bends around massive objects, a phenomenon known as gravitational lensing, and in the large-scale structure of the universe itself. But dark matter isn't the only silent architect. At the heart of nearly every large galaxy lies something even more mysterious, a supermassive black hole. These are not the small black holes formed by collapsing stars. Those are common, millions of them likely drift unseen through our own galaxy. No, supermassive black holes are different. They range from millions to billions of times the mass of the sun. They sit quietly at the centers of galaxies, invisible, unless they're actively feeding. Ours is called Sagittarius A, a quiet giant weighing in at about 4 million solar masses. It doesn't shine brightly like a quasar, but it's there, anchoring the Milky Way, subtly influencing the orbits of stars near the galactic center. We know it's there not because we can see it, but because of how it affects its surroundings. Astronomers have tracked stars orbiting an invisible point at incredible speeds, like moths circling an undetectable flame. But here's the fascinating part. Supermassive black holes seem to grow alongside their host galaxies. The bigger the galaxy, the more massive the central black hole tends to be. This correlation suggests that galaxies and their black holes aren't independent entities. They're partners in a long cosmic dance. How do they influence each other? When a supermassive black hole feeds, when gas and dust fall toward, it releases enormous amounts of energy, sometimes more energy than all the stars in the galaxy combined. This energy can heat up or blow away the surrounding gas, halting further star formation for millions of years. This process is known as feedback, and it plays a crucial role in shaping galaxies. Without it, some galaxies might have continued forming stars at an unsustainable rate, becoming far denser and more chaotic than we observe today. Black holes also regulate mergers. When two galaxies collide, Their central black holes often end up orbiting each other eventually, merging as well. These events send ripples through space-time, gravitational waves, detected by observatories like LIGO and Virgo Dot. So while black holes are often seen as destructive, cosmic drains swallowing everything nearby, they're more like galactic regulators. Quiet, mysterious, and incredibly influential. Together, dark matter and supermassive black holes, along with gravity, have shaped the universe we see today. They are the hidden hands behind the beauty of galaxies. They are the silent architects of the cosmos. And though we may never see them directly, we feel their presence in every glowing spiral and distant quasar, because without them, the universe would be a very different place, perhaps empty, perhaps formless, certainly not the one we call home. If you could pause time and look out into the universe from a quiet place far from city lights, what would you see? You'd see stars, of course, scattered like distant campfires across an infinite ocean of darkness. You'd see the soft glow of galaxies, some near, most unimaginably far. And if your eyes could see beyond visible light, you might even catch a glimpse of the ancient afterglow of the Big Bang itself. But here's the most astonishing part. When you look at those stars and galaxies, you aren't seeing them as they are now. You're seeing them as they were, sometimes thousands, millions, or even billions of years ago, because light, for all its incredible speed, still takes time to travel across space. And space is vast. So vast that the light we see from distant galaxies has been on the move for eons, crossing unimaginable distances before finally reaching our eyes or the mirrors of our telescopes. In a way, every night sky is a time machine. Every star you see is a memory. And with the right tools, powerful telescopes, and sensitive instruments, we can peer even deeper, peering back to a time when galaxies were just beginning to form. This is the gift of modern astronomy, not just to observe the cosmos, but to witness its history unfold. Let's begin with one of the most famous examples, the Hubble Deep Field. Back in 1995, astronomers pointed the Hubble Space Telescope at a small patch of sky, a region so dark and empty it seemed to contain nothing at all. They let the telescope stare at that tiny dot for 10 consecutive days, collecting faint photons that had traveled for billions of years. And what did they find? Thousands of galaxies, each containing billions of stars, packed into a space smaller than a grain of sand held at arm's length. Some of these galaxies were nearby, relatively speaking. Others were among the oldest ever seen, dating back nearly to the dawn of time itself. That image, the Hubble Deep Field, changed how we see the universe. It showed us that galaxies have been forming and evolving for most of cosmic history. And it proved that by looking far enough into space, we can look back far enough in time. Now, imagine doing that, but better. With the launch of the James Webb Space Telescope, JWST, in 2021, we've taken a giant leap forward in our ability to peer into the past. Unlike Hubble, which sees mostly invisible and ultraviolet light, James Webb is designed to see in infrared, the kind of light emitted by the earliest galaxies, stretched across space by the expansion of the universe. This stretching effect, known as redshift, happens because as the universe expands, the wavelength of light traveling through space gets stretched along with it. Light that was once visible becomes infrared, invisible to our eyes but detectable by telescopes like JWST. Already, the James Webb Telescope has shown us galaxies that existed just a few 100 million years after the Big Bang, less than 5% of the universe's current age. These galaxies are small, irregular, and chaotic, exactly what we'd expect from the early stages of cosmic formation. But some of them are also surprisingly mature. They appear more developed than models. predicted, suggesting that galaxy formation may have started earlier and evolved faster than we previously believed. This is reshaping our understanding of how quickly the universe organized itself after the Big Bang. So, how do we interpret these images? How do we translate pixels into stories? It starts with light. Every photon carries information about temperature, composition, motion, and distance. By analyzing this light, we can determine how old a galaxy is, how fast it's moving, what elements its stars contain, and even whether it's forming new stars. This is how we know that many of the galaxies we see in the distant past were actively creating stars at a furious rate, much more so than most galaxies today. These starburst galaxies were factories of creation, churning out stars hundreds of times faster than the Milky Way does now. But why were they so active? Because the early universe was denser, gas clouds were more abundant, gravity was stronger in localized regions, and mergers between protogalaxies were frequent. All of these factors contributed to intense bursts of star formation. Over time, as galaxies grew larger and merged, this frenetic pace slowed down. Gas supplies became more limited. Some galaxies ran out of fuel entirely, becoming red and dead, filled with aging stars, but no new ones being born. Our own Milky Way is still forming stars, though at a much slower rate than it once did. Eventually, like many large galaxies, it too will slow its pace, entering a quieter chapter of galactic life. But before we drift too far into the future, let's return to the present, or rather the past, because everything we see in the sky is a version of the past. The light from the sun takes about 8 minutes to reach Earth. That means we never see the sun as it is, only as it was 8 minutes ago. The nearest star system, Alpha Centauri, is over 4 light years away. So the light we see from it left more than 4 years ago, and the Andromeda galaxy, our closest large neighbor, is over 2.5 million light years away. The light we see from it began its journey long before humans walked the Earth. Imagine that. Beam of light leaving a distant galaxy, passing through the void, skimming past other galaxies, weaving through interstellar dust, bending slightly under the pull of gravity, and finally landing softly on the mirror of a telescope pointed at the sky. That single photon has traveled farther than any human ever could, carrying with it the story of a time when the universe was young, and now it rests in your mind. In the quiet of your evening, as you drift towards sleep, we are not just observers of the universe. We are participants in its unfolding story. We are made of stardust forged in ancient supernova. We live inside a galaxy that formed from the merging of countless others, and we are watching gently, patiently, as the universe continues to write its cosmic history. Through telescopes, we become time travelers. We peer into the past, not to change it, but to understand it. To learn where we came from. To see how galaxies were born, and to remember that even now, in this moment, the universe is still creating new. Stars are forming, new galaxies are colliding, new light is beginning its long journey across space. One day, perhaps billions of years from now, someone else, somewhere else, may catch that light, and they, too, may wonder, just as we do, just as we always have. The universe is not a museum. It's not a place where things are displayed behind glass, frozen in time, untouched by change. No, it's alive. It breathes. It moves. It creates. And nowhere is this more evident than in the galaxies we see today. They are not static islands of stars adrift in an endless sea. They are dynamic, evolving systems shaped by gravity, dark matter, black holes, and the ever-expanding fabric of space itself. Some galaxies burn brightly with new star formation, their spiral arms glowing blue with the light of young, hot stars. Others are quiet giants, ellipticals filled with ancient red stars, that have long since stopped forming new ones. And some are irregular, chaotic, still finding their shape, like cosmic adolescents trying on different identities. Each galaxy tells a story of birth, growth, collision, and sometimes decline. But even now, in this present moment of cosmic history, galaxies are still changing, still merging, still evolving because the universe is never done building. Let's begin by looking at what galaxies look like today, not just in our own neighborhood, but across the vast cosmic web. Our Milky Way, for example, is part of a small gathering of galaxies called the Local Group, which includes the Andromeda Galaxy M31, the Triangulum Galaxy M33, and dozens of smaller dwarf galaxies orbiting us like satellites. These galaxies are slowly drifting toward one another under mutual gravity, and in about 4 billion years, the Milky Way and Andromeda will merge to form a single giant elliptical galaxy, often referred to as Milkomeda or Milka. Yes, Milka, as in space yogurt. Scientists may be brilliant, but they're not always poetic. Still, this future merger is a reminder that galaxies don't live alone. They gather, they interact. They influence each other across millions of light years. Zoom out further and you'll find larger structures, galaxy clusters containing hundreds or even thousands of galaxies bound together by gravity. One of the nearest is the Virgo cluster, a sprawling metropolis of galaxies located about 54 million light years away. It's home to massive ellipticals, barred spirals, and everything in between. Even beyond clusters lie superclusters, the largest known structures in the universe. The Laniakea supercluster, our cosmic address, stretches over 500 million light years and contains roughly 100,000 galaxies. These superclusters form the skeleton of the universe, connected by filaments of dark matter and gas, with vast empty voids in between. This grand structure, the cosmic web, has been growing for billions of years. What began as tiny quantum fluctuations after the Big Bang has evolved into this immense network of galaxies, stretching across space like a luminous spider web. And yet, despite its size and complexity, this cosmic architecture is not eternal. Something else is happening, something that threatens to unravel the great galactic dance. That something is dark energy. We've mentioned dark matter before, the invisible scaffolding that helped the galaxies form. But dark energy is a different kind of mystery. Unlike dark matter, which pulls galaxies together through gravity, dark energy does the opposite. It pushes them apart. We don't fully understand what dark energy is. Some think it's a property of space itself. Others believe it could be a new fundamental force, but we do know this. The expansion of the universe is accelerating, and that changes everything. Billions of years from now, galaxies that aren't already gravitationally bound to us will drift so far away that their light will no longer reach us. They'll vanish from view entirely, not because they disappear, but because the space between us expands faster than light can travel. Imagine living in a future galaxy, isolated in a sea of darkness, with no signs of other galaxies around. You look up and see only your own stars, no distant glows, no swirling spirals, no evidence that the universe was ever anything more than a lonely place. To those future observers, the idea that the universe once contained trillions of galaxies might seem like myth, a story told by old telescopes and forgotten data. But back to the present. Today, galaxies continue to evolve. Some are still forming stars at a steady pace. Others have gone quiet, their gas reservoirs depleted or expelled by supernova or black hole feedback. In fact, astronomers classify galaxies based on their star-forming activity, star forming. Galaxies usually blue in color, rich in gas, and actively creating new stars. Quiescent galaxies, typically red, with little to no new star formation, often due to gas loss or consumption. This distinction isn't just aesthetic. It tells us about a galaxy's life cycle, whether it's still young and growing, or entering a quieter phase of existence. Take the Milky Way, for instance. We're still forming stars, about 1 or 2 per year, but not nearly as much as we used to. In a few billion years, we'll likely settle into a more quiescent state, joining the ranks of the so-called red and dead galaxies. Elliptical galaxies, especially the largest ones, are often found in dense regions of the universe galaxy, clusters where mergers are common. These galaxies tend to be older, redder, and less active in star formation, suggesting that their most creative days are behind them. But again, nothing in the universe is truly finished, even in these aging galaxies. There are exceptions. Sometimes a fresh influx of gas, perhaps from a passing satellite galaxy, reignites star formation. Or a central black hole wakes up, feeding on nearby material and sending jets of energy rippling through the galaxy. Galaxies may slow down, but they rarely stop completely. And then there are the outliers, the irregular galaxies, the dwarfs, the peculiar shapes that defy easy classification. Many of these are undergoing interactions, being pulled apart by gravitational tides, or experiencing bursts of star formation triggered by recent encounters. Some of the most fascinating galaxies we observe are caught mid-collision galaxies, like the antennae galaxies, where tidal tails stretch across space like glowing ribbons, and waves of new stars ignite in the compressed gas clouds. These collisions aren't destructive in the way we might imagine. Stars rarely collide directly. Space is too vast and stars too small. But the gravitational forces reshape entire galaxies, triggering bursts of star formation, altering orbits, and eventually leading to the birth of something entirely new. This is how many large elliptical galaxies were born, not through gentle accumulation, but through violent mergers of spirals. So while galaxies may appear serene in photographs, they are anything but peaceful. They move. They merge. They evolve. They are part of a cosmic ecosystem, a cycle of creation, transformation, and recombination that has been unfolding for 13.8 billion years. And it's still going as we peer deeper into the universe with telescopes like James Webb. We're seeing galaxies that existed just a few 100 million years after the Big Bang, small, chaotic, and bursting with star formation. These early galaxies are helping us piece together how quickly the universe learned to build structure, but we're also beginning to see hints that the era of galaxy formation may be winding down. Star formation in the universe peaked several billion years ago and has been declining ever since. Gas supplies are running low in many galaxies. Mergers are becoming rarer, and dark energy continues to push galaxies farther apart. Eventually, if nothing changes, galaxies may become isolated islands in a cold, dark cosmos, places where new stars are born, where only the oldest stars remain, and where the sky is filled with silence. But that's a very long way off. For now, galaxies continue to shine, they continue to evolve, they continue to tell their stories, not just to Jews, but to anyone who looks up and wonders. So tonight, as you drift towards sleep, remember this: you are made of galaxy stuff. You're a part of a story that began with the first flicker of light in the darkness. You live inside a galaxy that formed from the ashes of countless stars that lived and died before you were born. Somewhere far out in the cosmic web, two galaxies are beginning their slow, graceful dance, preparing to merge, to create, to become something new, just as they always have, just as they always will. We've drifted far tonight, from the first flicker of light after the Big Bang to the graceful spirals that now spin in silence across the sky. We've followed the long, winding path of galaxy formation, a journey written in stardust, gravity, and time. And yet